Ever tried putting together a puzzle with missing pieces? Or maybe you've noticed how your streaming service recommends movies you might like, even if it doesn't know you that well. These are examples of a bigger problem in science and technology, recovering missing information from incomplete data. Today, we're diving into a breakthrough method called RGNMR that's changing how we tackle this challenge. Let's start with the basics. Imagine you have a giant spreadsheet, like a grid of numbers, where most of the cells are blank. But you know that this grid has a hidden pattern. It's low rank, meaning it can be described with just a few underlying factors. For example, a movie recommendation system might use a low-rank matrix to represent user preferences and movie characteristics. But here's the catch. Some of the numbers you do see are wrong. Maybe a user accidentally rated a movie poorly, or there's a glitch in the data. This is the robust matrix completion problem. How do you recover the true values when some data is corrupted? Current methods struggle with three big issues. First, they often need way too many data points to work well. Second, if you guess the wrong rank, the number of underlying factors, they fail completely. And third, they can't handle matrices that are ill-conditioned. Think of them as math problems where tiny errors blow up into huge mistakes. Enter RGNMR. This new approach is like a smart puzzle solver that adapts as it goes. Here is how it works. 1. Guess and refine. RGNMR starts with an initial guess of the low-rank matrix. It then iteratively improves this guess by focusing on the data it trusts most. 2. Outlier detection. At each step, it identifies and removes the data points that seem most likely to be corrupted, like filtering out the noisy pieces of a puzzle. 3. Gauss-Newton magic. The method uses a mathematical trick called Gauss-Newton to refine its estimates, ensuring it converges quickly and reliably. What makes RGNMR special? It doesn't just handle missing data, it thrives in situations where other methods fail. For example, it can recover a matrix even if only 10% of the data is visible, or if the assumed rank is slightly off. And unlike older methods, it doesn't get thrown off by ill-conditioned matrices. The researchers tested RGNMR on everything from synthetic data to real-world problems like computer vision. In one experiment, they compared it to existing methods by trying to reconstruct a 3200 x 400 matrix. Think of it as a massive spreadsheet, with 5% of the values corrupted. While other methods failed badly, RGNMR nailed the reconstruction, even when the matrix was mathematically tricky. But here's the really exciting part. RGNMR isn't just a theoretical win. It comes with mathematical guarantees. The paper proves that under certain conditions, RGNMR will always find the correct answer. This is a big deal because it means scientists and engineers can trust it for critical applications, from medical imaging to financial modeling. So why does this matter to you? Think about the next time you stream a movie, use a navigation app, or see a photo restored from old film. These systems rely on recovering hidden patterns from incomplete data. RGNMR is a tool that makes that process faster, more accurate, and more robust. Let's break down the math. Matrix factorization is like splitting a spreadsheet into two simpler parts. One that captures the main pattern, a low-rank matrix, and another that catches the errors, a sparse matrix. Think of it as separating the signal from the noise. But how do we know this split is accurate? That's where the real magic happens. Mathematicians use norms to measure how big a matrix is. The Frobenius norm is like adding up all the squares of every number and taking a square root, essentially the matrix's total energy. Then there's the operator norm, which tells us the maximum stretch a matrix can give a vector. These tools are our rulers, helping us measure how close our reconstructed matrix is to the real one. Here's the kicker. When we use orthogonal matrices, which are like rotations or reflections that keep distances the same, the math stays stable. It's like building with blocks that never warp or bend. This ensures the rows of our matrices don't blow up into chaos, keeping everything predictable. The proof. It's like a set of guardrails. One lemma shows that if we focus on specific parts of the matrix, let's call them omega, the error in those areas stays tiny. Another connects the dots between the norms of individual columns and the whole matrix, proving the error shrinks under the right conditions. Together, they guarantee our reconstructed data is trustworthy. So next time you see a recommendation or a restored image, remember, it's not just luck. It's math working quietly in the background to turn chaos into clarity. Understanding these tools isn't just for scientists, it's a window into how we decode the world. And who knows? Maybe you'll be the one cracking the next big puzzle. Thanks for watching. If you want to dive deeper into the math or explore real-world applications, check the links below. Stay curious and keep exploring the hidden patterns in the data around you.